Humanity's knowledge of the universe extends 14 billion light years from the planet Earth. However, we only have physically travelled a fraction of 1 light year into space. One of the ways we're able to overcome this shortcoming in our experiences is by analysing the light that is emitted from distant objects. Light carries ample information across enormous distances and allows us to increase our understanding of our own position in the cosmos. By comparing the information that we receive from across the universe with data gathered here in a laboratory, we're able to expand our knowledge about far-off places without ever leaving Earth. One object that has received much of this attention is our own Sun. This project will detail the process of spectroscopy by showing how the information we gather from space is analysed and compared with our findings in the lab.
Okay, so the experiment we're going to be doing, the project we're going to be doing is on spectroscopy and the elements in the Sun and how they're related to the elements that we can find on Earth to see what chemicals are on the Sun. One way we do this is by using certain chemicals that are easy to identify by the distinctive colors that are emitted with bits of the chemical. When the bits of the chemicals are sprinkled onto a Bunsen burner, such as magnesium, and that's one of the experiments we're going to be doing today. And we're going to be seeing the emission lines that are emitted from this magnesium when it's burned on a Bunsen burner. And when we look at the Sun through a spectroscope or a spectrometer, we can see the same elements are found from the Bunsen burner, which means that the Sun has magnesium in it. The spectrum from a flame consists of a pattern of thin, bright spectral lines called emission lines, and this is against a dark background. The number of lines produced and the colors are unique to that element or compound that produces them. So right now we'll see what kind of light emissions are created from magnesium.
So here we are burning magnesium in a Bunsen burner.
Just ignite like this.
While the professor is burning the magnesium, Serena is capturing the emission line spectrum.
So that is a magnesium.
Yep, I see it.
Using the spectroscope.
This is the light signature for magnesium. On the bottom is the emission line spectrum that we see through a spectroscope while burning magnesium in the lab, as just demonstrated. This emission line spectrum consists of thin, bright lines. At the top of the absorption line spectrum we get when we capture the Sun's light with a spectroscope. The dark lines that break up the otherwise continuous spectrum are called absorption lines. These occur because the light of that wavelength has been absorbed by gases between the Sun and the viewer on the Earth. Emission lines of a gas occur at exactly the same wavelengths as the absorption lines of that gas. Because of this, we can compare the two spectra, match the emission lines with the absorption lines, and determine that magnesium makes up part of the Sun's chemical composition. Now we'll perform a similar experiment for hydrogen, using light from a hydrogen lamp.
So what we have here is the emission line spectrum of hydrogen viewed through a spectroscope. You can see the emission lines. And here's the lamp. And here's Serena.
This is the light signature for hydrogen, and again you can see the emission lines at the bottom looking much like they did when we filmed them through the spectroscope in the lab. These emission lines match the absorption lines in the top half of this graphic, again showing us that hydrogen is part of the Sun's chemical composition. Kirchhoff and Bunsen first performed many of these experiments in the mid-1800s. Thanks, laddies. Our modern-day thanks go out to Professor Asardaghi for his assistance with the experiments and the use of his lab and materials, and to Professor Kishimoto for imparting both his astronomical knowledge and his good taste in Hawaiian shirts.